Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on injection molding, troubleshooting, solving common part defects. My name is Sherry Cudd, if I can get it out today, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. I have a few quick, a few quick housekeeping items before we begin today. If you are watching us on YouTube, we encourage you to like and subscribe so you receive future notifications when Chase the Knowledge webinar recordings are posted. As for those who are listening live, thank you. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand using the react icon in the toolbar, and I will unmute you and call on you to ask your question out loud. We will answer all questions at the end of the webinar, so stay tuned. You can access and download PDF copies of this presentation, our product line card, common processing guide, and information on our technical engineering team in the materials section during the presentation. Once again, if you are attending live, a certificate of completion and a recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of the presentation and the handouts in the event you don't download them from the materials section. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We do encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted. Our next webinar topic is yet to be determined, but will likely happen in September and will be posted here for registration. You can subscribe or invite coworkers to subscribe, receive notifications of all future Chase the Knowledge webinars by clicking the subscribe to webinar notifications button at the top of the webinars page. As I mentioned, we are also on YouTube. Just search for Chase Plastics on YouTube to find our channel, where all Chase the Knowledge webinars are located and will be posted for easy viewing. Hit subscribe to be notified through YouTube when we post new content. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com, Chase the Knowledge blog, or under the resources tab, which is the easiest way to find it from the home page. As you can see, we have a live blog on common injection molding defects that we invite you to read. In addition to our presenter, Andrea Kendrick, whom I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to help ask and answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're likely very familiar with Andrea and the level of expertise that she brings to the table. So without further ado, Andrea.
Hey, good afternoon. Andrea Kendrick here. Today we're going to go over injection molding troubleshooting and some common part defects that you might see. So our agenda for today, we're going to do a brief overview on material itself. Then we're going to go over some prep considerations, drying, residence time, some plastics appearances, just so we really set the expectation for what to expect when you go to run these materials and what they might appear like or look like when you're done creating parts out of them. We'll go through our questions to ask, kind of a, hey, I'm having an issue. What do I need to consider? And then we're going to go over some of the common defects, what they look like, what might cause them, and what might be some remedies to help fix them. So we're going to start with going over plastics in general, just very briefly. So plastics overall is split generally into two different categories: thermoplastics, which is what we specialize in and what we're going to talk about, and thermosets. Thermosets have their own processing equipment and processes that I do not cover today, but it could be covered by other companies, right? But today we're going to focus specifically on thermoplastics, semicrystalline, and amorphous materials, and we'll go over them very briefly, just to get an understanding of how they differ and how then that might affect how they're going to process and what issues you might run into. So semicrystalline versus amorphous. Semicrystalline materials have dense, tightly packed regions known as crystals. They're called semicrystalline because they're only partially crystalline. Anywhere from 30 to 70% is where we'd put that. The other portion of it is going to be amorphous. So they do have those tightly packed regions. They also have portions of their makeup that is going to be amorphous in nature. And we'll get to why that's kind of important in the next couple slides. Then we have amorphous materials. The term a or an in front of a word will mean not or without. And then morphous means structural. So amorphous as a full definition means without structure. There's no tightly packed, dense regions of crystals. It's completely without structure, kind of like a plate of cooked spaghetti. Tends to be the analogies that get used pretty commonly here. So why is that important to us, or why do we need to know this type of information when we're talking about troubleshooting? Two things. Semicrystalline materials, they have what's known as a melting temperature. They're T sub M. And that is the distinct temperature at which we're breaking apart those crystal regions. So because those crystal regions exist within the material, we have to reach that temperature at least to make sure there's enough thermal energy to break apart those crystal regions. Then we go a little bit beyond that, and that's going to be where we're going to process those materials. And so we're not doing anything in terms of getting it to flow or creating good parts until we get past that TM. Okay. The second part that's pretty important to that is that because we have to break apart those crystals and those really tightly packed regions have to expand all the way out to get them to process correctly, flow by one another. When they go to cool down inside your mold, they're going to shrink a lot more because they want to get back to those original tightly packed structures. And so you're going to find that your semicrystalline materials are going to shrink a lot more than an amorphous material will. Could be important. Maybe you're running a mold, you're running an ABS material, and then all of a sudden you switch to a PA6, maybe a little bit better chemical resistance. For whatever reason, you may switch, and then you find, oh goodness, it's a big jump, big difference, because now we're running a material that has a much larger percentage of shrinkage compared to the amorphous counterpart that could have been used. For a rule of thumb, when we talk about semicrystalline materials, anywhere between 1 to 2% is a typical range for shrinkage. So 10 to 20 thou, pretty decent range, specifically when you consider the range I'll give you next for amorphous. So we have to hit the TM to make sure we break up those crystals. So we're processing it at the right temperature, and we have to note that it's going to shrink more. Also, because it's shrinking more, if we go and we shoot through the process, we make the mold a little too cold, whatever it may be, if we don't allow it to shrink appropriately, we have an even larger range of error potentially for shrinkage and warpage within semicrystalline parts. Okay, and then for amorphous, they don't have a TM. TM is specifically for crystal regions because amorphous materials do not have those. They do not have a TM that they need to hit. They have the TG, which semicrystalline materials have as well. It's when those molecules can start moving around. And so we're going to process above the TG, but we don't have a very specific point to hit when we talk about amorphous materials. So from a thermal standpoint, you generally have a little bit more of leeway with your amorphous materials compared to your semicrystalline. And I'll show a chart on the next page for that. The other part is because they're not expanding as much because they don't have those super tightly packed regions, they don't have to contract as much upon cooling. They do not shrink as much as semi-crystalline materials do. So the range, if you recall from the last page, 1 to 2% for semi-crystalline, we're in the 0.3 to 0.7% range, very typical. So 3 to 7 thou compared to 10 to 20 thou. So big difference in range. And so if you're finding that you're switching from one material to another, or you've only ever ran propylene products and all of a sudden you're running ABS, or you've only ever ran polystyrenes and now you're running a nylon 6, you're going to find that that difference in going from an amorphous to a semi-crystalline or vice versa could play a bit of a role in what issues you could potentially be seeing because of that. Okay, so for the chart that I mentioned, we kind of see our temperature chart here. This kind of gives you a DSC map of the different thermal points of your materials. So you can see here your TM in this location here. So my melting temperature, I'm breaking apart those crystals. And so you have this little processing window here from where it's going to have enough thermal energy. The crystal regions are broken apart. And then you have degradation temperature. So somewhere in this range, this is where we're telling you to process in terms of temperature for a semi-crystalline. Your amorphous material, again, no TM. And so you're looking above the TG out to degradation temperature. So generally a larger processing window thermally for your amorphous versus your semi-crystalline. It's why we'll be quite cautious when we talk about semi-crystalline materials. Hit that temperature that's recommended. Don't go too much higher than that because we're going to start butting up against that degradation temperature. And so you can start having some issues. So really try to stick with the recommended temperature that's given for the product material that you are processing. Okay. So from that standpoint, now let's get into shrinkage a little bit. The common processing guide that Sherry had mentioned that's attached to this presentation or that you could get from our website separately, you'll see there's a column specific for mold shrinkage. And so that is included there for all the different materials. If you're not sure if it's semi-crystalline or amorphous, if you look at it, it kind of folds into one of the two ranges given, kind of gives you an idea of where it's at. But regardless, the guide does give you good recommendations as a general rule of thumb on the shrinkage values you are to expect. Note that these are also unfilled. Everything except for the PPS material, these are all unfilled. You have a glass filled product, changes the shrinkage. You'd have to account for that. So, but mold shrinkage information on here. Also, you'll notice what's on here, which we'll skip when we get to the next page, is going to be your drying recommendations. So now that we kind of understand semi-crystalline versus amorphous and shrinkage and our thermal sensitivity, we don't want to get too hot on our semi-crystallines. We don't want to get too hot on either of them, but not too hot on our semi-crystallines. So now let's get into drying. Drying is probably one of the biggest issues you're going to find or have issue with when it comes to our hygroscopic materials. They're going to be probably the #1 culprit for issues when running these materials. So hygroscopic as a term refers to anything that's going to absorb moisture from the air. So when we use it, we're referring to the material itself. The material is hygroscopic. It absorbs moisture from the air. These materials, because they are taking in that moisture into their matrix, they need to be dried before you can process them. So if you try to run them before they are adequately dried, you're going to run into issues like splay or potentially even breaking up of the polymer chains, which can cause performance problems. And so a lot of issues can come from not adequately drying. And so those of you guys that have ran nylon materials, I'm sure you've ran into it a time or two where it presents a problem because they're not dried appropriately. So we make sure that we dry it correctly. You'll also find that along with the recommended shrinkage, the recommended mold temperature and melt temperature, any of your hygroscopic materials should also come with recommended drying temperatures and times. So it gives you the correct temperature and time to drive out the moisture to get it to an acceptable level before you process the material. So that's going to be something that we want to make sure that we're really paying attention to and that we're also really drying the material correctly. So just a little bit more on that. The other thing to note is you can over dry some materials. Materials like nylon use moisture a little bit to help plasticize it. It helps it flow a little bit, gives it a little bit of flexibility. If you dry it too much, it actually becomes more brittle. So you have a problem there. Your material can turn brown. If you leave it in there for an extended period of time, it's turning brown. You might start kind of burning it a little bit. You can also create pellets that become a solid mass because then they dry together into a solid mass. And that will be quite difficult to feed through your machine if that's happening. So we want to make sure we don't over dry it. We want to follow the recommendation, follow the times that they give us, and do what is being recommended for the material we're getting ready to run. A way to tell if we're properly dried, some of the ways to tell would be we're not getting any popping or snapping if we're doing a purge shot out of the barrel. We're not seeing any splay. That's a big one. If you're getting visual defect splay on your part, clearly there's a problem with moisture there. So we want to make sure we're not getting that. And then lastly, which would be the most accurate way to tell, would be if you have a moisture analyzer. So if you're able to analyze it beforehand, you would also be given a recommended moisture value to stay under, equal to, or under for these materials. If you take an analysis, you do a test of it, yep, it's below where it's supposed to be, awesome, out we go, and we're running it and should be running into no issues, hopefully, from a drying perspective. Pictures of that. I don't have splay further on as one of the defects necessarily, but we are kind of talking about it right now. So you can see in this particular part, you can see all those kind of lines there. That's going to be splay that's displaying itself in the part because this material was not adequately dried. And so issue here. And then you'll see they used a lot of material. They did dry it correctly. None of those problems were shown because it was dried correctly. And so big issue with a lot of our hygroscopic materials not being dried adequately and splay being a really big defect that we see pretty commonly. So we want to make sure that we're drying our material before we run it. A quick side note, or I guess an additional note, I should say, we always recommend you dry hygroscopic materials because they pick up moisture. It could affect them. It could break up their chains based on their chemistry. Always will recommend it. You might still get recommended to dry the material even if it is not the hygroscopic material. Reason being, you might accumulate a little bit of moisture on the surface of the pellets. And so if you're moving it from one climate to another, maybe you get some of that moisture building up on the surface, and then it still gets into your machine, could still cause a problem. Now, it might not necessarily break up the chains of the material, but you're still going to have that unnecessary moisture and steam and gas that shows up that could end up being a problem. So you can get burns, some gassing. You might have some mechanical properties if it gets really intense, and visual defects that could be a problem. So again, we're always going to recommend you dry your hygroscopic materials to the right one, but it might also be recommended that you dry non-hygroscopic as well to adjust for potential surface moisture. Okay. And then lastly, for moisture, the last point I want to point out is nylon being the biggest, I want to say culprit, but the one that's going to be generally the most impacted by moisture, or that we're going to see the most issues with nylon. Moisture is a little unique in nylon in that, as I mentioned, it plasticizes it. And so what you'll also find is it helps it flow a little bit. And if you condition it, so you get it up to a certain level of moisture, 50% humidity, you'll find it also makes it a little more flexible of a material. And so in some cases, if you want to make sure it's not getting brittle, or if you're using an impact modified material, this particular one is not, but if you used an impact modified material and you want to get really good impact performance out of it or bolster that a little bit, you might also condition your parts as well after the fact. And so just another way that moisture can affect our material. And so you might see that. And where maybe you run parts one time, maybe they got conditioned and we didn't know about it. They're performing great. Impact is awesome. But then all of a sudden the next lot comes in and it's not performing as well. Maybe that one wasn't conditioned during packaging or shipment or whatever it may be. And so that's just another thing to think about or to be considering when we're working with nylons specifically. Okay, next one, as a quick little thing to think about, is going to be our residence time. So residence time is really how much time does the material spend in the barrel itself. And so we want to know how much of the barrel are we consuming with one shot. Ideally, we're in that 20 to 80% range. So a shot takes up 20 to 80%. And then ideal really being like half, 50%. Because we want to make sure the material's in there long enough to get a real good melt, get a real good mix, but we don't want it to be in there so long that the heat that the material is on does any type of damage. We don't want it to break down any of the additives that are in the material or even just break down the material itself. So we really want to make sure that we're very cognizant of how long it's staying in there. And the other thing is that different polymers will also react differently to it. So some are going to be a little more resilient. Some are going to be allowed to be in there a little bit longer. They're a little more lenient in terms of heat and leaving them in a barrel. Materials like polyethylenes and propylenes tend to be a little more resilient. You can get away with a little bit longer residence time. So you could get down to lower barrel usage. Again, it's not what we recommend, but you can get away with it a little bit versus something like a PVC which is not as very thermally stable. So you're going to end up with shorter residence time. Or you might find materials like maybe your ABS is working great and you're getting great parts out of it. Now you use an FR ABS. Well, the FR package in the ABS is a little more sensitive. And so you might not get away with that extended, maybe you're up close to 10 minutes for residence time. Maybe you can't get away with that with an FR ABS and you're experiencing issues. And you go, well, I got regular ABS, it was fine. Well, the FR package now is the problem. And so we want to make sure we're aware that we're not allowing the material to sit in there for an extended period of time, because the heat that is on the material can cause damage to either the additives or the material itself. All right, and then just if you guys have been to my presentations in the past, I've given some of these examples before. If you've never used the material or ran the material that you're getting ready to run, I want to point out a few different things in terms of the actual appearance of the material. So you're not going, oh, well, it shouldn't look like that. That's a problem. In some cases, it might look like that. That might be how it's kind of supposed to look like or what it's going to look like. And maybe you haven't ran it before, so you're not sure. So up top, you can kind of see a difference between like an SMMA or really a PC would be in kind of that range where you can see it's not very hazy. You can kind of see through it really nicely. Versus like a random clarified propylene, you get a little bit of that haze there. And so if you run a random clarified propylene and you're expecting the crystal clear zero haze that you get out of something like a PC, that's not going to happen. And so it's not an issue. You didn't run into a problem necessarily unless it's very dramatic, then maybe a contamination problem. But the expectation is there's going to be a little bit of a haze there. And so if you know that going into it, you see that tiny bit of haze, you go, oh, that's normal. That makes sense. Next would be materials like PPS. PPS, your branch type are going to have this darker brown color to them. And so when you go to color them something else, if you want them in different colors, you're fighting a brown. And so if you see this and you're like, well, that's not a very vibrant purple. Yeah, that's the color you're going to get because you're fighting a brown to start with. So it's not an issue. That's just the way it looks. And then additional ones, moly-filled nylon 6/6, unfilled PEI. This is standard PEI. That's what it looks like. It's got kind of this amberish color to it. And so you didn't burn it. There's no burns. There's no degradation. That's just what the material looks like. And so, which in that case, I mean, a lot of these, the pellets should match that. You should see that, but that is what it looks like naturally. And then lastly, a glass-filled versus an unfilled product. This particular one is for 6/6, but you're going to kind of find that across the board. You can get a lot more polished, a little bit shinier of a surface out of an unfilled product. As soon as you add the glass, breaks up the surface a little bit, gives you kind of a rougher finish. And so that's normal. So if you've ran unfilled for a long time, then all of a sudden you're running glass filled, it's going to look a little rougher. It's not going to have that really nice, super polished look. There are some materials that maintain a more polished look, like the PARA would hide glass a little bit better and give you a nice polished look, but you're still adding a bunch of glass that wants to break up the surface. So note that there will be a little bit of a different appearance there. So we want to keep that in mind when we're running these materials. Okay, so troubleshooting questions to ask. So you run into an issue, you're having a hard time running a part, your material is running into a problem. These are some of the questions that hopefully you're able to ask yourself first and determine the answers to, because in the grand scheme of troubleshooting, the idea is to pinpoint where the issue is coming from. So if we can kind of go through these questions and figure out where we think it could be coming from, it makes it easier to troubleshoot overall. The other thing I'd like to point out before we get super far into it is when it comes to troubleshooting, every mold is different, every machine is different, and every material is a little bit different. Even different lots could be slightly different, which could be the problem. Who knows? But I do want to point out that every situation is different. And so not all of these are going to be, I should say, none of these are going to be a one size fits all. So also as I get into the defects as well, that give you some possible solutions and some possible causes, note that every machine, every mold, every location is going to be a little different. And so if you're not finding that any of the solutions offered or suggested are working, maybe that's the time to work with someone that could go and personalize and step through a troubleshooting process with you. People at Chase would love to be able to assist you with something like that. So please feel free to reach out. Okay, so some questions to ask. Is this a new problem and a new material? So I've never ran this material before, and it's a brand new problem, or I guess I should say it's a problem because you've never ran it before, but it's a brand new problem. So could it be that the wrong material was being selected for this application? So what's the problem? Oh, the part was a little too brittle made out of this material. Well, maybe the material was the wrong choice for that particular one. Could it be that the mold was not designed for the shrink or the flow of that resin? Polycarbonate materials push harder, and so they need a little more leeway, a little bit more openings for your gates to get it to flow through nicely compared to maybe an ABS you've used in the past. So maybe an adjustment needs to be made or to be thought about being made when we go to run it. Is this a new problem but an existing tool? So we've been running this for a while and now we're having a problem. Could it be that there is wear in your mold that's causing an issue? Could the process have changed a little bit? Could the new lot of material potentially be an issue? That's where we would be looking at to try to pinpoint where the problem is coming from. Is it the same material, same tool, but in a new press? Is it smaller or larger? Is it affecting the residence time or changing it? Was there a dedicated dryer on the last one and not for this one? There could be a few different things that could be causing this potential issue. Is this problem consistent across multiple lots of material, or is just one lot of material giving you a problem? If it's consistent across a lot of lots, it could be the material is the wrong material. It could be that it was just the wrong one selected for that. Or if it's just one particular lot, it's likely that maybe that particular lot is the problem. And so a few things to think about there. And then lastly, as a general overall one would be if we're blending or using an additive, if we're running it and we're having issues, can we run it or have we ran it without the additive or color? If it persists without the color, well, then maybe the material is a problem. Maybe the mold is a problem. Maybe the process is a problem. But if it persists, it means that, well, the additive and color is not the problem. If it is no longer there when you run it without it, well, then something about the additive or the colorant that's being used is not working well in that base material. Maybe it's the wrong base. Maybe it's, for whatever reason, maybe it can't withstand the temperature the base material is being ran at. For whatever reason, it's potential that the colorant or additive is the problem. So all these questions we're just trying to ask to get an idea of where can we pinpoint where this issue might be coming from. And so when you start troubleshooting with someone, they might ask a lot of questions. They might say, hey, can you talk about your processing? Can you tell me what you did, what you changed, what it helped with, what it didn't help with? Because again, every problem is quite unique. And so we're just doing our best to get to the bottom of it and see if we can figure out where that problem is stemming from and seeing if we can fix it. Okay, so now getting into the actual defects themselves, we're going to start with black specks. And so this is typically to be kind of your carbon kind of burnt up, but your black specks here is what they look like in a clear part, or you can see in the pellet specifically there. But some potential causes for your black specks, generally it's going to be degraded material or contamination in the material. And so you might commonly see that in materials like PC. We've got that really tiny black specks that might be in them that you might find. So as we go through all of the potential causes and solutions, we'll kind of break them down based on if it's maybe a mold issue, a machine issue, a material issue, or a process issue. Again, you can see there's a lot of suggested causes because, again, everything is quite unique. So I'm not going to read through all of them. There's a lot on every page. Please feel free to download this and look it up and use it kind of as a guide to help you with troubleshooting. But you'll see typically if there's going to be a mold problem or cause for this, it's generally going to happen if you have a hot runner system where you've got a dead spot. So it'll catch some of the material, burn it up, and then release it back into the part when it is grabbed. Machine issues, maybe you've got a leaking check ring, you've got some screw wear, maybe the nozzle is the wrong type, maybe the wrong screws being used for that particular material, or maybe you have a hang-up area. Again, grabbing some of that material, it's getting burned up because it's not able to go anywhere, it stays there too long, and then it gets released back into the material as it flows over, and you get a black speck. Material causes, if it's contaminated, or if you have degradation from either polymer or the additive, which could happen if you degrade it in your dryer, you're running it a little too long, but typically you'll see it's a contamination issue or something within the process of making the material could be an issue also. But again, if we point that out, if you see in the pellets, it's probably a quick one to go, well, the material obviously is a problem, right? Some process causes, temperatures may be too high, residence time may be too long, and so we want to make sure that we're keeping those in check. And so with that, again, laundry list of potential solutions, all of them regarding making sure that your equipment is clean, making sure your material is being ran dry, and making sure there's no contamination or hang up areas where this material could kind of get stuck and then get popped back in as a problem. And then for contamination, things to consider if you're adding in regrind, or if you're using grinders or dryers, any of that are also being used for other materials, there's a potential that that had a couple leftover pellets, got into your process, burned up at the temperature you're running your new material, and got in there. So we just want to make sure everything's clean and we're starting from fresh, or if possible, have dedicated dryers or machines for certain products. And so there's no contamination across that. Okay, gate blush. And so this is gonna be kind of like a hazy, off, non-polished area that you're gonna find around your gate. So this is typically caused by a material flow issue. A lot of times you'll find that the gate is too small, or it's being gated into the wrong area. Maybe the section's a little too thick for it, or you might find that there's not enough venting. There's some trapped air in there. And so if the machine is not providing your velocity that you're asking it for, or if you've got a thermocouple that's misbehaving or overriding, if the material is a little too wet, the viscosity is a little too low, all these different things could be messing with or causing a flow issue that could result in the gate blush. You might find that the material, the mold temperature is too cold, your melt temperature, might be too high or too low. And because you can see some of these causes are on the extreme in either direction, a lot of times when we do questions or we work on troubleshooting with customers, we'll ask, hey, what have you tried? And has it fixed it or made it worse? Because then we can figure out, okay, maybe one extreme is the wrong answer, but maybe the other one is the right answer. And so we always try to get an idea of what's helped or not helped when you're walking through trying to figure this one out. So some adjustments, increase your gate size, maybe try increasing or decreasing your melt temperature, change the mold temperature. If you're gating into a really thick section, it might be needed that we change the gate location. And so a few different options there to try to remedy this particular problem. Burns. And so this one, pretty self-explanatory in terms of what it's going to look like. It's going to look like it's burned. So in this case, kind of a clearish part. You see burns throughout the clear part. And these ones, you've got more opaque parts. Very dramatic burn on this particular one. But burns typically caused by trapped gases or material degrading, either because the heat was too high or there was too much shear. But regardless, we're burning it. And the thing to note here is there is the potential to damage your tool if we're allowing it to continue to run. And so if it's super dramatic, like the first picture, obviously we're on it and we want to make sure we fix that. But even small little burns in certain areas, if it's consistently happening in that area, you could start to cause damage to your tool, which then could potentially be an expensive fix. So we want to make sure that we're addressing it quickly. So some causes could be your gate design could be wrong. If it's got too much shear or heat coming through it, could be burning it. If you have a malfunction in the machine, maybe the heat is going too high, it's running away. Maybe your velocity is not right. If you have wet or contaminated material, this could happen, could cause a problem. If we're injecting it too fast or the residence time is too long, you might see burns happening because, again, it's being damaged or degrading because of heat and or shear. In this case, there's generally twofold, as mentioned, dieseling or degradation. There's also then for dieseling itself is more of a vent issue. And so it could be caused from the temperature or the shear being too high, which was the last slide. This one talks about vents. And so if the vents are crushed or they are dirty and they're not allowing that air to get out or to escape, you might find that it gets stuck in there and then it burns the part. You could have, again, still wet or contaminated material could be making this worse, but this one's, a lot of it has to do with vent issues because it's trapping it there. We also make sure we have adequate venting as well. So we want to make sure that that's adequate there too. So some recommendations: ensure proper venting. Make sure it's the right size, make sure it's clean, make sure they're not crushed, make sure they're working. And then we want to just make sure we're not adding unnecessary heat or shear to the material, because then it could cause some of this degradation and this burning. additional pictures so they can look like a little bit of everything. The one was very dramatic and it was super large all the way across the top. Sometimes it's as little as small ones at the end of fill that you find. Could be anything, but if you're burning the part, something's happening somewhere. Got to figure it out. Got to stop it. Okay. Bubbles is the next one. So if you're seeing bubbles in your parts, these are be commonly seen in your materials that you can kind of see through. It's a little harder to check or find a bubble in your opaque parts, but if you're molding your clear parts and you're getting bubbles in your part and you're able to see it, we want to work through the process of figuring it out and fixing it. So typically when you see this, it's going to be caused by trapped gas. And so it gets trapped, closed in there, and you end up with bubble or bubbles in your part. A lot of times it will come down to vents being plugged. Maybe we have excessive pressure. We have overheating material. Maybe the material is wet. If it's wet, it's got moisture in it. Putting out the steam as it's being ran hot could be causing a problem. We might be injecting it too fast. Whatever we're doing, we're trapping air within the part as it's trying to be molded. We want to make sure we're not doing that. So the best way for this particular one is if we're consistently getting a bubble kind of in that area, maybe we want to do a short shot study and we want to progress through it and see where is this developing and seeing what is happening at that time at that area and see if we can fix what we need to fix to get it to stop doing that. If it's maybe not as consistent, maybe it's the material is wet and so you're getting that moisture coming off the material when it's being ran hot. Or in other cases, if it's consistent, you might find some of these other ones could help as well. So reduce our melt temperature, reduce our tonnage if we've got too much pressure going on, make sure we have proper venting again, make sure they're clean, adequate sized and placed correctly. And then make sure that we're increasing our back pressure compression ratio. Make sure that we're getting the air out, whether it be from the process or from the vents being adequate as well. So a few different things to try there to try to figure it out. But again, doing a short shot to figure out where it's starting and then work our way from there. And then flash, this one's quite dramatic in this picture specifically, but flash is going to be excess material around the parting line or the features of it. And to know if it's happening super in the same area and very commonly, it could be a result of tool damage, or it's because we're shoving too much material into the cavity itself. And so those are generally your two causes of flash specifically. So big one would be mold damage. So if you've not had an issue with flash before, and all of a sudden you're getting it and you're getting it pretty consistently, and you know that you've been running this tool for a minute, it's potential that you've got some wearing going on and some damage that's happening in the mold itself that's causing a space to be there for the material to get into. And so check to make sure that you don't have a damaged mold that's causing a problem. Wet or contaminated material, if it's super wet and it's flowing super easy, maybe it's flowing into that area and it shouldn't be, could be a problem there too. But overall, it could be that we are shoving a lot of material into the mold and we're really not supposed to, or there's damage that's happening. So we want to check those two first and make sure that we're addressing those. So recommendations, trying to reduce our melt and mold temperature to see if we're not, getting it a little too hot and trying to get to flow a little too easily. Clean the parting line, check to make sure that there's no damage, make sure the material is dried correctly. And then if none of those work, there's some additional ones that from the process that you could attempt to see if you have any problems that are causing that. Short shots, or sometimes they'll call them non-fills, generally kind of right at your end of fills when you typically see that, but it's not fully completing the shot. It's not fully filling out. This is because we're not getting enough material into the actual cavity itself. So what might be causing that could be a few different things, but the overall cause is we're just not getting enough material in there. And so venting could be a problem. The mold could be too cold, so we're trying to run it in there. It's kind of freezing off a little bit as it's flowing in there. We could be experiencing some heater problems. So maybe the heater is not working. The material is not getting hot enough to flow adequately. You could have material that's too dry, like a nylon. It doesn't flow as well. If it's over dried, you could have contaminated material, maybe a new lot of material that has a way different viscosity than previous ones, whatever it may be. What we want to make sure in this case for a short shot is that we have a robust enough process to account for the slight changes in viscosity. We'll have lot to lot. And so if we don't have a good setup for that, we don't have a good cushion, we might find that the change in viscosity of the material could affect something like this, could affect getting a short shot for the material. We could be underpacking it. We could be not using enough back pressure. Our melt temperature could be low. Our transfer could be too high, transferring a little too soon. And so a few different things that could be causing it here. But again, overall, we're just not getting enough material into the cavity. So how do we fix that? Figure out what's going on. So recommendations here are going to be making sure you have your proper cushion, again, to make up for a slight change in viscosity between lots that could be there. We want to increase our melt and mold temperatures. We want to make sure it's flowing well. So kind of the opposite of flash. So flash was we're putting too much in. We want to make sure we're not overflowing it in or any of that. In this case, we're not getting enough in. So maybe we have to increase our temperatures, get it to flow a little easier, and try to fill it out. Make sure we're getting there. And then some other ones, stuff like a flow leader or some other additional ones could be that it's just difficult maybe to fill that last little bit of fill. And maybe we have to make adjustments to make it there. So we want to make sure our temperatures are high enough, material's not too dry, so it's running correctly. And then a few other ones that could be issues as well. Make sure we got good venting, all of that. Make sure the material gets in there to make a full part. Okay. Jetting, sometimes called snaking. I typically just hear jetting though. And so you've got kind of this flow behavior pattern that you get coming through it. This is generally caused from your injection rate being too high for the viscosity of the material. So you're trying to get it to flow and the viscosity of the material is not quite agreeing with it. So a few things that could be causing it. It could be that your gate is too small or in the wrong location. So again, maybe you're gating into a thick section. So you can see that kind of appeared a couple times. So gating into a thick section can cause a few different issues. So this being one of them. We want to make sure that the machine is giving the correct velocity that we're requesting or we're trying to get it to. We want to make sure it's doing that. You could have wet or viscosity being too low of material, so it's flowing a little too easier for where it's opening up into the mold itself. And so your velocity through the gate is too high. You could try potentially slowing down, going through a little slower. Your mold is too cold. Your mold temperature could be too high or too low. Again, one of those things where it could be an extreme one way or the other. So we might ask, hey, have you tried one or the other to see if you saw an improvement one way or the other? But essentially, the viscosity going through that gate is not right for the material and for the part at that area. So we might try reducing our injection rate. We might try increasing the gate size. We could move the gate potentially. That one's a little more of an expensive afterthought fix. Ideally, if we can, we're trying the small fixes that don't require huge changes to see if it fixes the problem first, with then kind of our mold adjustments being kind of the last result or last ditch effort in which all these other ones haven't worked, because that comes with a price tag, changing your mold. So we want to try potentially injection rate change, increase your melt temperature. We want to make sure that the material is not wet. So a few different things to work on the speed it's coming in and the viscosity of the material. Sink marks. So those are going to be kind of those sink marks there, kind of sinks into the part. This is going to be because it's shrinking away from the mold surface. So a few reasons for that could be some hot spots, improper cooling, not great venting. You could have a leaking check ring. Your barrel could be too hot. Could be some contamination. There could be no cushion. So it's almost like it's not fully filled. You don't have an opening in it anymore, but not enough material is fully getting in there. Insufficient back pressure. Your transfer position could be incorrect. And so a few different things that you could try to see if we can get and fix that with it. So make sure we have a good cushion. You saw this in the other one. We want to make sure we have a good cushion to adjust for any slight variation in viscosity the material might be experiencing. So again, we want to make sure we have that robust process in place and maintain a good cushion for it. We want to make sure we have good screw recovery time. We want to potentially increase our pack and hold time or pressure to make sure that we're keeping the pressure on it, make sure it doesn't sink away from the mold while it's cooling and packing. And then maybe potentially reducing some temperatures, because if it's still hot, then it wants to pull towards that hot material. And so maybe we reduce temperatures a little bit, see if that helps. And then some last ditch efforts would be if it's a very thick part and there's nothing you can do about that area, maybe we add a foaming agent, reduce something or a flow leader to where we can get it to flow into that area and get enough material in there to really stay and pack in there and not sink away from the tool. So a few options there. We would, of course, try maybe the processing ones first, see if we can solve the issue, and then some additional options to try after the fact. And with that, that was the last defect that I talked about. If there is enough interest, we could potentially do another one on some maybe less common defects. And so if that's something that could be of interest for you, I would love that you would put that in a survey, because we would love to get to do another one. But with this time, that is all for me. Thank you, guys.
Great. Thank you, Andrea, again for your comprehensive presentation, as always. At this time, if you have any questions, please type them into the questions section of your toolbar, or raise your hand and I will unmute your microphone. I see we have a few raised hands, so we'll get to those first here in just a moment. We do have Jason Merkel, our technical manager, on hand to assist Andrea with questions today. As a reminder, as you type your questions, please remember to complete the survey at the end of this webinar. Your responses will help shape future Chase the Knowledge webinars, including, like Andrea was just talking, we may do a part 2 to this one if there's enough interest in doing that. But we always welcome your feedback. Also, please be sure to check out our webinars page at chaseplastics.com/webinars for past webinar recordings and future webinar announcements and registration. If you would like to have a custom Chase the Knowledge topic presented to your organization, again, please reach out to Andrea or myself. So Jason, I'm going to start with a few hands we have raised here. Let's see here if I can find Tom. Tom, I'm going to unmute you. Enable mic. Tom, can you? This is for Tom Wood, which actually I think he just hopped off. So, Jason, if you want to go ahead and take some questions, and then I'll let you know if I see any more hands pop up.
Yeah, no problem. All right, Andrea, we got a handful here to start. We'll see if
Oh,
any
there.
more.
I'm sorry.
Go ahead,
Tom,
Terry.
I'm going to ask to unmute you. I see you there now.
Guys, I was just trying to see who was asking questions, so I apologize. I didn't have a question.
Oh, okay. No worries.
Right,
All
but
right.
I think you did a great job. I think we're very well done and a lot of great detail. So thank you.
Great.
Thank you.
Tom.
Thanks, Tom. All right. Any other hands up for now?
Nope, that was the only one I was seeing.
Okay, perfect. All right, Andrea, first question is it a good idea to consider a moisture analysis in plastic granules before molding, or is it preferable for produced parts?
The moisture analysis,
Correct.
we would recommend that you do it on pellets before you run it, because you want to make sure you get the moisture to an acceptable level before you run it in the machine. You could do it on the part afterwards if you really wanted to, but the idea is to make sure it's at an adequate level or a low enough level to run it without issue.
Thank you. Next question is regarding root cause analysis. Is there an ideal method for root cause analysis of bubbles?
So for root cause analysis, we typically see, if we're getting really formal with it, we do a whole 8D type thing. We don't, our suppliers do with the materials, right? That's the formal way of approaching it. Ideally, if we're seeing that there's an issue with the part, an engineer is getting involved, we're working through your process, we're seeing if there's stuff that could be adjusted and fixed it ahead of time. Because typically once we get really formal 8D, we're at the point where we're thinking it's a full material issue, which it could be, but generally you're getting involved with an engineer that can help work through the process of seeing if there's any process changes or drying changes or whatever it may be to get the material to run appropriately and make good parts.
I'll go one step further on that. You know, there's several causes for bubbles in parts, and let's use clear material as a starting point, because obviously that's where we tend to see them the most, unless it's, you know, a pronounced actually raised bubble within the part, right? Which we might see in an opaque part. But if there's bubbles within a part, there's a couple ways of getting there, which Andrea kind of outlined. You know, is it voids or is it trapped gas? And those two things are formed to very different ways, right? So voids tend to be a measure of differential part cooling, typically held within thick areas or hotter areas of the part, where the part material is drawn to the outside of the part and therefore leaves a void in the middle of it, which results in a bubble. These tend to be larger, sometimes less uniform in shape, depending on the geometry of the part, where maybe the void will mimic whatever the curvature of the part is. That's a different phenomenon than what we would see with, trapped gas bubbles, which may be prone due to either using too much decompression or suckback during processing, which may introduce air into the melt, or if maybe the melt wasn't compressed enough prior to injection, which we would look to adjust via back pressure. In regards to the trapped gas, tends to be smaller bubbles, more uniform. They tend to be more circular for that matter, and sometimes they're grouped, so voids tend to be a little more in suspect areas, the thicker walls of the part, where at times the trapped gas looks different in both appearance and location. So we can draw some conclusions about what it might be, but a lot of times it just takes getting to adjusting the process to really figure out what was the ultimate cause rather than being able to identify by sight alone. Next question, Andrea, is just really about, can we get a copy of the slides, as there were some folks with this customer that weren't able to make it in real time.
And yes, I will, Andrea will be sending out an email with the slides. If you're still on the call, you can download the slides from the materials section above, but everybody who attended today will get a copy of the recording sent to them, as well as Andrea's presentation.
And any of the ones that you might have had and maybe misplaced, feel free to reach out. We'd be happy to resend them for this presentation, for previous presentations, any of them. We'd be happy to share again.
Next question is, if there are bubbles in the runner but not the part, should we try to eliminate or just keep producing as is?
I guess we'd want to kind of know where it's coming from. The nice part is it's not affecting your part specifically, but if there's the potential that it could end up in the part, we might want to probably address it, figure out what's causing it, and eliminate it if possible. So that way there is no chance for it to end up in the part.
Sometimes we see that if the runner or sprue specifically is of a thicker nature than the part, if it's just a void, then it might not be as problematic. If there is, air somehow being introduced into the melt in a way that could cause future problems with that, should that air transmit into the part cavity itself, somewhere along the process or with processing changes, then yeah, we'd love to troubleshoot that out. So I guess it depends a little bit on the nature of the design. But just like other things we hold within the sprue and runner system, like cold slug wells and what have you, if we can keep the defect out of the part, then it might be smooth sailing regardless, but we try to take it on a case-by-case basis. Let's see here. We have one question about someone with a picture of a defect. They would like to send that in. I would say probably best way to do that would be to send it to Andrea's email address you see here on the screen, and then we can pull in other more regional members of our technical team for further conversation and assistance as needed.
Absolutely.
Next question, Andrea, is can you comment on what's a bubble versus a sink?
So I think you kind of answered that one a little bit. I think it was more of the bubble versus void, because you're getting it more on the interior of the part itself versus the sink. The sink is pulled in from the surface and it pulls it in a little bit. So there's nothing inside it that's the problem. You have your bubble versus your void, where you have the space there that's caused either from air in the melt or from the material pulling apart towards the heat and creating a void. So it's more of a difference there than the sink itself, because the sink is more of just sinking away from the surface. So that you'll see right on the surface versus your void or bubble that's inside.
Next question, Andrea. This customer has a one cavity part and the legs on the part are in spec, but the body is not. Do we have any recommendations on that?
Yes, but a couple questions first, probably. In spec would be the questions of, is it out of spec because it's undersized or oversized? Is there a warpage issue? So they're not hitting a flatness that they need. We would need a little more information to help with that, because then from there we could figure out, cool, if it's undersized, we'd probably have a certain way of addressing it. If it's oversized, we'd have a way of addressing it. And if it was warping, we would have a different way of addressing it. So if the person that asked the question, if they wanted to send me a note and or a picture, that would be great. And we can work through it on that individual basis.
Yeah, we want to take that in stride. I mean, if we assume that this is dimensional spec, right, it's going to come down to what's the material, how's the part gated, what's the flow length look like, how's it situated in the tool, can we fix it with differential cooling from one half being hotter or colder than the other? Or do we need to focus on a gate seal study and adjust pack and hold to see if we can, get the body of the part to adjust differently than what you're seeing with the legs. So there's a number of levers we could pull, but to Andrea's point, we'd love to get a closer look at it to figure out what our best starting point would be. This is just a note, but I think it's worth mentioning probably for the group, Andrea. The question is just a note or observation, but why do most material moisture recommendations say 0.2, which I find to be high for processing?
0.2 tends to be the recommendation for nylon, generally, is what you find. And that one typically is a range, and generally even then we keep it on the closer side. So a lot of nylons you'll see in some of the guides, they'll tell you 0.05 to 0.2. 0.2 is generally pretty high, because by the time you go to run it, if you just checked it at 0.2, within 20-30 minutes you're probably looking at it going past that. So really they might say that as the range. We might push you more towards the 0.05 to maybe 0.1. We want to keep you much closer to the lower end of that, specifically for nylon, because that tends to be the one that's near that range.
Next question, Andrea, is how often typically is preventative maintenance preferred?
For the, I'm sorry, I didn't hear fully. For the machine, for the mold, for any of it, I guess.
Didn't specify necessarily. Yeah, I would say maybe we can take that one offline. If you have any specifics you're looking for on preventative maintenance, whether it's tooling or machinery, let us know. We'd want to look at, everything from material being used. It's, to know if it's prone to off gassing or what have you, or number of shots per tool, number of cavities, hot runner versus cold runner. There's a number of aspects we want to look at. We can try to dial in a more specific answer for you there.
Filled, unfilled, glass filled products, glass is abrasive. Might be looking at it a little more often. So yeah, lots of considerations.
Can you comment on what T sub M and T sub G are again?
I'm sorry, comment on what?
TM and TG, what they are and their differences.
Sure. So TM and TG are thermal transition points for our materials. The T sub G is glass transition temperature. So it's a temperature at which when you heat up, there's enough thermal energy that the molecules within the materials can start to move a little bit. So when you have an amorphous material that has no crystal regions, the glass transition temperature is the only one thermal point it's going to have. It's going to kind of dictate when the molecules can start moving around. For an amorphous material, again, with only a TG, for a performance standpoint and a thermal standpoint, we keep our applications for that below the TG. And then for processing, we obviously go above it. So we melt it, it can flow. The T sub M, your melt temperature, is going to be the temperature at which there's finally now enough thermal energy to break apart the crystal regions within the polymer itself. And each individual material, be it amorphous with TG or semicrystalline with TG or TM, are going to have their own individual temperatures at which those are occurring. So an example like PA6 is going to have a TG around 50 degrees C and a TM around 220. So you'd find that we would process above the 220 to make sure we're hitting that TM and then going above it a bit. And then a material like a polycarbonate that's amorphous would have a TG around 130C. And so we'd process, generally you see a decent little jump above the TG for the what temperature we're going to process it at. It does kind of get a little bit confusing because we call it a melt or processing temperature on a data sheet. And that's the temperature we actually want you to set it at or to have your melt actually hit. If you were to test it and see what temperature the material is experiencing in your mold, that melt temperature is not to be confused with the thermal transition point, T sub M, which is specific for the crystal regions within a semicrystalline material. And for that particular question, love that. We also did one of the presentations I did that we covered for Plastics 101. There's quite a few slides on it. So if you want to shoot me a note, I can send you that presentation. So there's some additional slides on those as well.
Next question, Andrea, is if you mold glass-filled nylon below 0.5% moisture, how do you know without testing parts if they will be too brittle?
Too brittle, I think is what you said.
Mm-hmm.
You'll see it won't flow as well. So you might see some differences in pressure because it's not flowing as well. But really the big one is going to be because they become more brittle, they're going to not perform as well. And so even with the glass-filled product, you might find that it's maybe breaking a little sooner than it should. And so the brittle performance is really going to be a big show there, and potentially some processing variations because it's not flowing as well as it should.
Yeah, I hate to sound overly gray on this topic, but it really is super part specific because there's, many parts that probably could be molded below that 0.5% threshold. And if it's not having any stresses during molding, despite, an increase in viscosity, it may not be a problem at all. And as long as the material's not been degraded, despite being dried to that low of a moisture content, it might not be a problem, period. Because if there's no stresses during molding and you put that part back in the ambient temperature, it's going to reabsorb that moisture. That's the interesting thing about hygroscopic resins and especially nylons is that they regain moisture as easily as they lose them during drying. And again, during the life cycle of a part, so a part molded in June today, maybe very ductile coming out of the tool or, a week or so out of the tool. We're molding the same part in December, could have lost all of its moisture and could be more brittle at that time as well. So I guess the short answer to your question is there's not really a great way to know without testing unless you're seeing hesitancy to fill, to Andrea's point, in terms of high injection pressures or anything like that. But even those pressures wouldn't always indicate that there's a material brittleness problem. It would be very much part specific.
I think that might have been our last question. Jason, do you see any others we didn't
I
get
believe
to?
you're correct.
All right. We would like to thank all of you for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We do hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information is posted right there on your screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar in September. Thank you.